Okay, welcome back. So in the last lecture, we introduced methods for solving the Schrodinger equation that was based on expanding the wave function onto a suitable basis, and then diagonalizing the matrix resulting from matrix elements between different basis elements. These are called overlap matrix elements. And we use that to study the transitions, sorry, the wave function for a double wave problem. Right. So basically, our main finding was that the wave function has a structure like this for the ground state, and a structure like this for the first excited state. That was the first finding of the previous lecture. A second finding of the previous lecture was that the energy gap between the first two states was much smaller than, say, the energy gap between all other states. So if I were to draw the spectrum, I would draw it this way. I have the ground state. The precise value of the ground states depends, of course, on where you put the zero of the potential. So this is really relative to the zero of the potential, as usual. I have a first excited state that is nearly degenerate. And then I have all other states somewhere up in the spectrum. And what we were finding is that the difference between the first excited states and the ground state was pushed towards zero when the barrier was becoming higher and higher. And in the limit of infinite barrier, where you have an infinitely steep barrier, you have basically two independent harmonic oscillators. If this barrier becomes very, very large, and basically you have two independent harmonic oscillators, then E1 was becoming essentially equal to E0. So this is, in a nutshell, the result of last lecture. In this lecture, I want to explore the consequence of this finding to define a notion of a process or phenomenon that is quite important in quantum mechanics, that is called quantum tunneling. What is quantum tunneling? Quantum tunneling is a phenomenon according to which a system can cross a barrier traveling in energetically classically unallowed regions. Okay, it sounds fancy, but in practice, it means something like this. Suppose I have a double wave system, or any system where it contains an energy barrier. And suppose I have an energy, my system is in an energy state much lower than the barrier. For instance, is in the ground state, or in the first excited state. Let's suppose it's in the ground state. Well, classically, there is no such a thing as ground state. Classically, you can say you have an energy, and this energy naught is much smaller than delta U, where delta U is this. Right? Quantum mechanically, of course, you have only certain allowed energies, the quantized energy, and you can be in any of them as long as the distance between this and this, the energy is much smaller than the band. Now, classically, we've seen what happens to a particle with such an energy state. It will basically be confined to this region. These are called classical inversion points. When the particle approaches the point in which the energy becomes equal to the potential energy, then clearly the kinetic energy must be zero, so the system stops. And it cannot go any further because it would have an imaginary velocity. So the only thing they can do is to travel backwards. So the system, develops orbits in this region. Now, what we're going to discover, so if you start with a particle, classically, if you start with a particle here at some time t, and you ask, am I going to find a particle on the other side of the barrier at any time? Well, clearly in classical mechanics, the answer is you're never going to find a particle on the other side of the barrier, because that would involve traveling into a classically forbidden region with imaginary velocity. Yeah, this is completely nonsense classical. And in fact, if I take I don't know, my ball, basketball, and I throw it towards the wall, there is an energy barrier to go on the other side of the wall. And no matter how many times I try, the chances that I cross the barrier and I find myself I find the basketball in my kid's room, which is behind the wall, is 0. I can continue forever, and the ball will always bounce back to me, assuming that the wall doesn't crash and the ball doesn't, that the ball holds in a good physical condition. A quantum particle, however, does cross the wall every so often. And this phenomenon of sort of penetrating the barrier rhetorically and ended up on the other side is called quantum tunneling. Now, quantum tunneling seems a very exotic phenomenon, but it plays a crucial role in many processes, fundamental processes as well. The most relevant, perhaps, for the community of students that sign up for a degree in quantitative and computational biology is, of course, the chemical bond. We will discover that basically electrons tunnel continuously between different atoms, and by doing that, they lower the energy if they can continue tunneling, therefore forcing the atom to stay together. That's a big statement. I mean, basically, matter as we know it at these energy scales exists because of this phenomenon. But at a more fundamental level, and talking about physics that probably you're not particularly familiar or interested in, even the fact that we have a mass, a significant mass, comes from mostly from tunneling phenomena in subatomic physics. If there were not such a tunneling phenomena, the proton would have much more mass. Basically, would be massless. Would have a mass maybe. So let me check. 10 MeV divided by 1 GeV means 1/100th of its own mass. Would be a 100 times smaller. So matter as we know it wouldn't exist. So quantum tunneling is a central phenomenon. So with the mathematical equipment we developed so far, we can already describe quantum phenomena and give you a hint of quantum mechanics, explanation of this kind of an exotic phenomenon that occurs in the microscopic world. So how do we do it? We will take a simplified description. We can say, okay, the particle can be on the left or on the right. And I don't really care which point on the left the particle is, because I'm not interested really in computing the probability of finding the particle here or here or here or here. What I'm really interested in is finding the particle on the left versus finding the particle on the right. So what they're going to consider is that the particle can be in either of the following states at any time. So I'm interested in basically two states. Left states is the left eigenfunction that I use to solve the tunneling problem. If you haven't seen this, go back and rewind the last lecture. And the right state is the corresponding right eigenstate of the harmonic oscillator right here that we used when we solved this problem. So I'm gonna use these two states as a representation of my Hilbert space. It's a very low dimensional representation of the Hilbert space. The Hilbert space is infinite dimensional, but we already discussed that these two states capture the essence of it as far as the slow, low energy state is concerned. So if I'm only interested in looking at low energy states with very little energy, I can go along with these two states only. I don't need the entire infinite dimensional space. And I know that I can write the Hamiltonian in this space. And the Hamiltonian in this space looks like a 2x2 matrices with some elements, 1/2 h bar omega, 1/2 h bar omega, and then epsilon and epsilon, where epsilon is small. And this can be calculated from the barrier, but I don't really need to have an exact numerical value for this. I can simply say, I'm looking at a system with this Hamiltonian and this things. Now, I know that this Hamiltonian can be diagonalized, and there are two states. The ground state is going to be 1/√2 left plus right. And the first excited state is going to be 1/√2 left minus right. Okay. Now, this is a summary of basically everything we have said so far. So now the question that we want to address, that is actually the key question to define the quantum tunneling phenomenon, is the following. Given that if the state of my, if some initial time t0, let me set it to 0, the initial state of my system is in the left, what is the probability to find a system in the right state at time t? So writing this in the language of probability, I'm interested in this conditional probability, the probability of finding the particle in the right part of the value at time t, condition that it was on the left at time t0. So in classical mechanics, this is actually 0, because the particle can never cross the barrier. So I never find it on the right. In quantum mechanics, we'll see. These are called Rabi oscillations, and we'll now compute it. So what do we do? Remember, we look at the probability of finding the particle in the right at time t modulo square. Right, so we can write this actually with a bracket notation as right psi t modulo square. That's the probability of finding the particle in the right side of the barrier at time t. Now, this, of course, I don't know, but I do know that a particle was in the left at time t0. So all I need to do is to evolve, to encode this information and use the Schrödinger equation to calculate the state at time t, provided I know the state at time t0. So let me draw it in a cartoon. I know that at time t0, the system was in left, and I want to compute the state at time t. Now, if left was an eigenstate of the Hamiltonian, that would be very, very simple, because I have already discussed in a previous lecture that the eigenstates of the Hamiltonian never change, remain stationary with time. In other words, if I put a system in an eigenstate of the Hamiltonian and go and take a coffee, I'm guaranteed that, no matter how long my coffee will take, when I come back from my coffee, the system will be still in the same quantum state. But this is true only for the eigenstates of the Hamiltonian and eigenstates of any operator that commutes with the Hamiltonian. But in general, when states are not eigenstates of the Hamiltonian, the time evolution will drift away the state from an eigenstate of Hamiltonian to, in general, a linear superposition of states of the Hamiltonian. So psi, in general, would be a linear superposition of states of the Hamiltonians. And in general, would be a linear superposition of states of left and right. Left and right wave function, for instance. So the question is, computing this linear superposition. So in one of the previous lectures, I already discussed the notion of time evolution operator, which is basically equivalent to using the Schrödinger equation, because the time evolution operator is basically a solution of the Schrödinger equation. So this quantity right here I can write it in the following way. I have my Hamiltonian, t minus t naught is set to 0, so I don't care. And then a wave function times t naught. Right? And I know that at time t naught, the system was in the left state. So now I've formulated the problem. Knowing that the system was in time t naught equals 0 in the left state, I have written a mathematical object that evolves the state until time t, and it's this time evolution operator. And I'm looking at the probability to find a system in the right at time t. Okay? Now, the problem, you see, is that this guy here, the Hamiltonian, is now an operator that acts on this 2 by 2 state. This is the matrix that I defined before, because in this space, the matrix is, remember, 1/2 h bar omega, epsilon, 1/2 h bar omega. Now, how do I compute the exponent of a matrix times this state? And obviously, this is not something, remember, when I say e to the some matrix, I mean the identity plus the matrix plus 1/2 the matrix multiplied by itself twice, plus and so on and so forth, with all the infinite many terms. Right? So either I evaluate infinitely many matrix vector multiplication, which would take me an infinite amount of time, and I cannot do that, or I find my way through using some smart trick. So, however, so the trick here is to write the left eigenstates, the left states as a linear combination of eigenstates of the Hamiltonian. So let me remind you that the right eigenstates of the Hamiltonian is left, sorry, the ground states of the Hamiltonian is left plus right, and the first excited state of the Hamiltonian is, say, left minus right or right minus left. It doesn't matter, because remember the states can be defined up to a constant or a phase, so I don't care whether it's right minus left or left minus right. Now, if I sum these two guys, I can use these two guys and say, okay, I can say the following: root of 2, and now I know that the left eigenstate is 1 over root of 2 psi naught plus psi 1 yes, and the right I state is 1 over root of 2 psi naught minus psi 1. And you can immediately see that this makes sense because remember, my ground state is like this, and my first excited state is like this. So if I sum these two cancel, and I'm left only with this state. And if I sum these two, and if I take the difference, these two cancel, and I'm left only with the right state. So that's what this linear combination is giving us. Okay, so now with this in mind, the idea is to write this term here as 1 over root of 2 ground state plus first excited state. So if I do that, my probability to find a particle at r at time t, condition equal to left at time naught, it's going to be the square modulus of the right exponent negative I over h bar t, my matrix. And then now I have 1 over root of 2 psi 1 psi 0 plus 1 over root of 2 psi 1 square, modulus square. Now I have to compute the exponent of the Hamiltonian, but now on psi naught. And see, I'm going to be a little bit pedantic and repeat something I already mentioned in the lecture before. Now, like I said, this is like you see, you have all these terms acting on psi naught. And you have infinitely many of them. But now I can evaluate all of them at once because you see, the Hamiltonian always, I can evaluate all of them at once because they act not on a generic state, and then I would have to have matrix elements, matrix vector multiplication. But they act on the ground state of the same Hamiltonian, so that means that, in particular, this is going to be E naught. This is going to be E naught squared, and so on and so forth. So what I get after I compute all of them, I replace every time I see a Hamiltonian, I can put the corresponding eigenvalues. Now this becomes a series of numbers, no longer a series of matrices. And when I resum the series of numbers, all I get is the same expression I had before, but rather than having the Hamiltonian there, I now have the energy. And this is now a number, complex number. And of course, the same thing happens when instead of the ground state, I have the first excited state. Then it is, I get the first excited state. So with this in mind, I can go on this line here, continue from here on the next line and saying this is the square modulo of R. Now I get e to the negative I over h bar e naught t times 1 over root of 2 psi naught plus, well, let me put this outside, psi naught here, 1 over root of 2 plus, right, e to the I over h bar e1 t, and then I get c1, 1 over root of 2. Now, these are now numbers, and they can be taken out. So, still being a little bit pedantic, but why not? I mean, this is going to be, first term is going to be e to the negative I e naught t over h bar, root of 2. And then I'm going to have right psi naught plus e to the negative I e1 t divided by h bar, root of 2, right psi 1 square. Now, to evaluate this, let me remind you that this is r, and the psi naught is again 1 over root of 2 left plus right. And therefore, this contraction will be 0, because left and right are nearly orthogonal. And this contraction will be nearly 1. So I get 1 over root of 2. And if I do right psi 1 as a negative sign there. And therefore, if I do it with psi 1, I should get a negative sign here. I should get negative 1 over root of 2. Okay, so let me summarize this. This is 1 over root of 2. And I get a negative, and this is 1 over root of 2. Okay, so essentially what we have found so far is this. So now it's only a matter of computing this matrix element. And so this will give me a 1/4. And then now let me just evaluate this square modulus by taking, very trivially doing all the calculation. And I multiply by the complex conjugate. Now, let's do this. It's 1/4. This times this is going to be 1. This times this is going to be 1. So I get 1 minus 1. No, there's a plus. Sorry. Okay, so I get a 2. And then I get 2 negative signs. This times this is going to be negative of e to the negative I over h naught, e naught minus e1 t. And I get this times this, I get negative e to the minus e of h bar. And this time I get e1 over e naught, or I can say e naught minus e1 with a plus sign, t. Okay. Now, I expect this to happen because the imaginary part have to cancel out. So let's do all the calculations in place. I get a 2, I get a minus a cosine of a naught minus e1 divided by h bar over t, plus sign of this argument, which I don't care because it will cancel with the opposite sign coming from the imaginary part of this guy, which has an opposite face. So I can take away the imaginary part. No surprise. This is a square modulus. The imaginary parts must disappear, and so all I get is a 2 here for the real part. So we're getting close to an end. So basically what we're finding, I'm canceling this upper part here, and it's quite impressive. We got 2/4, so it's going to be 1/2, 1 minus cosine of E0 minus E1, or if you want E1 minus E0, it doesn't matter, cosine is an even function, divided by 2. I hope I've done all the calculation correctly. I might miss a sign, maybe not, maybe it's all fine. So, in fact, there's a probably, I don't know, is this 1/2? Yeah, maybe, I don't know. There could be a question about whether this 1/2 is correct or not, but I think overall it's correct. So if I were to plot this, it's clearly at time 0, the cosine is 1, and this starts from 1, as it should. But as the time goes by, obviously this cosine begins to grow until it reaches, sorry, it begins to fall until it reaches 0 and continues to -1. So this will go to 1 at some point and then go back. So basically what we're discovering is the probability for a system to be found on the opposite side of the barrier oscillates with time with a characteristic frequency which is of the order of the energy difference between the states in units of h bar. So in particular, when the barrier is extremely high, then the frequency becomes essentially 0, and this curve becomes almost flat, and you never see a transition. But when the barrier is lowered, then the frequency becomes finite, and you begin to observe this oscillation. So basically, it means that the system spends an equal amount of time on the left and the right, as you would expect from symmetry arguments. The potential is symmetric. If you do enough crosses, you lose memory of many crosses you've done. In the end, if you wait long enough, you should spend half of their time on the left and half on the right. Right. And in fact, if the system is in minimal energy configuration, it has equal probability to be found here and here. And in any energy configurations, in fact, the probability to be found on the left and on the right is the same. Even it can, but you know, the question is what happens if I start from the left? So I find this exercise interesting for many reasons. First of all, that it tells you that the eigenstates, you can have a system prepared in a state that is not an eigenstate of the Hamiltonian. The left state is not an eigenstate of the Hamiltonian. So the eigenstates of the Hamiltonian enter when you want to understand how the system evolves in time. That's what this exercise is telling us, very generally. That it's useful to know the eigenstates of the Hamiltonian because they are, if you know the spectrum of the Hamiltonian, the eigenstates and the eigenvalues, then you can predict how the system evolves in time. But it doesn't mean that you can only be found in an eigenstates of the Hamiltonian. You know, you can ask the question, what is the probability to be on the left and on the right? And since the left state is not an eigenstate of the Hamiltonian, the system won't remain in the left forever, but it'll go on the right too. And in this case, it does that with a regular frequency. So you see this is an interesting exercise because it tells you how dynamics works in quantum mechanics, which is in a highly counterintuitive with what you expect to classical mechanics. The system oscillates across the barrier. And now these oscillations are only determined by the barrier and they have a characteristic frequency. Now, for these reasons, these quantum oscillations are used by clocks to determine, set the time, because they are set by quantum mechanics. It's the characteristic frequency set by quantum mechanics. So just as much as the pendulum uses a characteristic oscillation of gravity to determine to split the time in equal intervals, quantum tunneling clocks use a characteristic oscillations of quantum states to set the time for their measuring time intervals. There is one important observation I'd like to close this exercise. And it's the following. If you look at the two problems, one in which I have an infinite barrier, then and you compare it with the one in which you have a finite barrier. If you go back on the exercise where we were evaluating the energies, you will discover that, the energy was of the two states, E1 and E2, were degenerate in this limit. But when you sort of lower the value of the barrier to a finite amount, you would have a splitting. Oops, trying to use the other color. Splitting into a first and excited state, right? This is E0 plus epsilon, and this is this E0 was actually H bar omega. Now, I want to focus here on one particular thing, the presence of quantum tunneling. So the presence of a finite barrier, which is, if you have a finite barrier, then this frequency is finite, and therefore you have quantum tunneling. So the presence of quantum tunneling is associated with the lowering of the energy ground state. If you compare to the case in which the barrier is so high that there is not effectively any tunneling, the ground state of the system with a finite barrier is lower in energy than the ground state of the system with an infinite barrier, which means that allowing tunneling basically lowers the energy of the system, is energetically favorable. And now this is ultimately, as we shall see in the second part of the course, the reason why chemical bonds exist. Because allowing the electron to tunnel between different atoms, to be shared by the atoms, effectively lowers the energy. So it's that systems like to be close enough to be able to share electrons, because by tunneling through different atoms, electrons lower the energy. So it's anytime the system evolves towards a lower energetic state, that is actually favorable. So I think this exercise has told us quite a few things, and I suggest you try to do that yourself. The mathematics is not that hard. You should be able to follow this mathematics and be able to do this exercise, okay? And we'll teach you a great deal about the origin of tunneling, the implications of tunneling, and especially the energetic implications. Okay, goodbye.